thank you for the introduction, and thanks for the organizer and the invitation. So it's my pleasure to give the talk here. So in this talk, I will talk about the rigidity conjecture and with some techniques using index theorem method with corners. So I think most of the results have already mentioned, but in this talk, I will mostly explain the details. Okay, so the theorems already been mentioned above, but just recall you a little bit. Let me state it again. So the main theorem I will talk about this time is just the version here, a comparison version. So suppose that we have two remaining manifolds with corners, okay, and F from N to M is a smooth spin map. And here smooth means it can be slightly extended to some set outside N and M for manifolds corners. And spin here means like the pullback, the tangent bundle of N tensor product with pullback of M is a spin bundle. And for the comparison condition, we need the following assumption for the map and the matrix. So first, we need the curvature form, and the second form, the form are non-negative. And then F is area decreasing, area non-increasing, and this on the whole manifold, and distance non-increasing in the boundary. Okay, and the critical part is the comparison condition for scalar curvature, mean curvature, and dihedral angles. Here we assume that all the dihedral angles are less than or equal to pi. For example, this holds for convex polyhedrons. So well, so far we don't know how to deal with the, for example, the concave angles. Well, yeah, and the last condition, I just write here the degree is non-zero. For example, we assume that M and N are of the same dimension. If different, that will be replaced by the A hat degree. And M has non-zero or characteristic. This last condition is to somehow ensure that the index is non-zero. So if all of the above holds the blue, brown, and red conditions, then we'll see that the red inequalities have to be equal. And we do have some more rigidity results, and maybe see if I have time, so I can say later. And I want to mention that this smooth condition can actually be relaxed. We can actually consider more general version like for the polyhedrons. So I will not talk about today, but I just mentioned it here. But mostly today I will look at manifold with corners. Okay. All right. So here's the outline of the proof. It requires two parts. The first is a comparison formula. It's a green formula for scalar curvature, mean curvature, and dihedral angles. And then the most important part is the index theory of manifold with corners. So the key fact of the Dirac operator or the index theory is the essential self-adjointness. And with the help of this, we can show that the Dirac operator with some boundary condition is essential self-adjoint and the Fredholm. And we can talk about the index. And to compute the index, we need the whole multiple invariance and under the condition of essential self-adjointness. Okay, so let me first be brief on the first part, which has already been mentioned by Zhizhang, so maybe I will be quick on it. So we'll just let me cheat a little bit. Let's assume that M and N are of even dimensional manifolds, and both of them are spin. Okay, this is just an easy assumption, and F is also spin map. Okay, so in that case, we can talk about the spinner of M and spinner of N, the two spinner bundles. And with the map F, we can talk about the connection on the tensor product manifold. And here we use a pullback connection from M. And then we can define the Dirac operator in this form on this tensor product bundle. Okay, now everything is even dimensional. Okay, and now we have a following computation, a green formula for it. Assume the blue condition and the brown condition. Furthermore, the dihedral angles are less than or equal to pi. Then for a smooth section of this vector bundle, then we have the following like green formula. So left-hand side is a norm of the Dirac, and the right-hand side is this guy's roughly speaking is gradient. And the scalar curvature comparisons here, mean curvature comparisons here, and here's a dihedral angle comparison, but the integral is taken on codimension 2 faces. And we have extra term, the integral of phi and phi was applied on the boundary Dirac here. D boundary stands for the boundary Dirac operator made by the boundary information of each phase. And later on, this will be killed by the boundary condition. So roughly speaking, this D comes from the original D by looking at the commutator with the modification of the normal vector. And indeed, this D boundary actually commutes or anti-commutes with the normal vector. And the commutator will give us the mean curvature comparison. So here, these two parts actually come from the classical estimate of Goethe and Semmelmann, or even the paper of Lott. Okay, now I will briefly explain the rest of the two terms. So for first, the angle terms comes from actually a smooth approximation near the angles. So let's look at the baby version, a 2D case. So near the codimension 2 edge, here it's just an angle. And the second fundamental form, where in the 2D case is called the geodesic curvature. It's just a curvature of this arc, which is 1 over r. Well, the rest of the part is just the original manifold, so that would be the same. Here, the curvature will diverge at the order of 1 over r. And in the higher dimensional case, if we look at the codimension 2 edge, this second fundamental form will also diverge, but it will be dominated by the vectors that is orthogonal to the edge. And on the other hand, the curvature will diverge, but the volume, here is just the length of it, it's also a very small term. Here in this case, it's just r times pi minus theta. Here, pi minus theta is the turning angle here. This guy is pi minus theta, and this guy is theta. Okay, it's primary school geometry, right? And after you try to multiply the two, integrate these two, you will get the r and r1 over r canceled. So what's left is a dihedral angle pi minus theta. So this is the reason why we have a minus sign here, because the pi just canceled. So what's left is minus theta. And for higher dimensional, well, it's similar. The curvature is still of 1 over r, but the volume, you can think of it like a part of the sphere. The volume will be smaller than r, like r squared or r cubed and so on. So this may explain why the higher dimensional will not appear in the form. Okay, I think so. That's for the angle term, and for the boundary Dirac term, we can kill this by the boundary condition. We define the following boundary condition on each face. So it's given here. These are the day-to grading on spinors for even dimensional spinors, and this En bar and En are the corresponding normal vectors on different spaces, different faces of n and m on the corresponding position. And we assume that this operator applies on phi is negative phi on each face. Okay. All right. It looks a little bit long, but actually you can think about this example in mind. If the two manifolds are exactly the same, and the two metrics are exactly the same, then it's a classical fact that spinor tensor spinor is naturally identified with forms. So in this case, the boundary condition, well, now this En bar and En are the same. So the boundary condition is nothing but the subbundle of forms only made by tangent vectors along the face. So I want to mention that also in this case, the Dirac operator is nothing but the theorem operator. So this kind of boundary condition is really called the absolute boundary condition. And for this case, it will give the index like the Euler characteristic, at least for manifold smooth boundary. Okay. So the good point of this boundary condition is that it can kill the boundary Dirac term. So in other words, the boundary Dirac will map the bundle B to its orthogonal complement. Therefore, this number will be 0 for at least smooth sections. Okay, so in summary, if we have a smooth section satisfied all the boundary conditions, then we will have exactly the formula. So left hand is D norm, and right hand side will have scalar curvature, mean curvature, and angles compared. Okay, that I think this finishes the first part. So for the questions. Okay, now let's come to the index part. So so let me first give a overlook of the index theory. So overview of the index theory. So the main results is the following. First, we will need to compute the index of the Dirac operator with respect to the boundary condition. In general, there will be a lot of subtlety in that because this is a manifold with corner. Even when a boundary, there will be subtlety, and for corners, there will be lots of singularities. So it requires works to talk about its index or really make sense of that operator. And to compute the index, we really need the homotopy invariance. But this we have to also develop this theory for manifold with corners. So let me state the results. So first, the first theorem is about homotopy invariance that we can compute the index. Suppose we have a family of boundary conditions, or that we can change the boundary condition, okay, where each of the BIT is a continuous path of subbundle of this bundle on the ith face. Here, I mean, a continuous path of bundles means the orthogonal projection is continuous. But I want to emphasize that we allow the boundary condition to change for independently for each face. Okay. And now we can also have a family of Dirac operators of that form. For example, when you change a metric, you get different Dirac operators. And the K condition here is that the D with respect to the boundary condition is essentially self-adjoint. And its domain is H1 Sobolev space. I will explain what I mean by exponential self-adjoint later. I think you know what I mean by H1, just a like function completed by its L2 and its L2 or norm of the derivatives. Sorry for that. And here, the last component I write here means the H1 sections lie in the boundary condition for on each face. Because for H1, the tree theorem allows us to talk about its restriction to the boundary as at least an H1 half section. But here we don't need some L2 information yet. But in any case, for the H1 half section lies in the boundary condition. So if we have the above path, then this essential self-adjoint is important here, then the index is the same, so that we can compute it by deforming everything to a manifold smooth box. Okay, and to ensure the essential self-adjointness, we need a criterion on that, and it's given by the following theorem. Suppose we have the angle condition here. So recall that this actually appears exactly in the theorem, the sigma theorem, that the angle of the domain is less than or equal to the angle of the target. And we also assume that they are both less than or equal to pi. If the angle condition is satisfied, then the Dirac operator with the boundary condition is essentially self-adjoint. And the domain is H1 with this space, with the boundary condition, and furthermore, it's Fredholm. Okay, and with help of the two results, we can compute the index by deforming the two manifolds. But we have to assume that along the deformation, the angle condition is always satisfied, so that they're all essentially self-adjoint, so that they'll change the index, and then we'll find that the index computed by the formula here, for at least for manifold with smooth boundaries. Then we know the index of origin. Okay. So far, any questions for the results? All right. Now let me explain what I mean by essentially self-adjoint. So actually here, the Dirac operator, you can think about the unbounded operator from L to the L2, and there usually be subtlety to talk about the index theory or whatever, anything about an unbounded operator. So for example, spectral decomposition, and although it's formally self-adjoint or symmetric, but it may not be essentially self-adjoint. So the definition is here. Let's denote this space, say infinity 0, 0, okay, to be the smooth sections that satisfy the boundary conditions and vanish near codimension 2 edges. So think about the 3D picture. You have a polyhedron, like or you have a polyhedron. Then we need this section to satisfy the boundary condition on each face and vanish near each edge, as well as the corner, as well as the vertices, of course. Okay, and this set or this smooth sections can be seen as a domain of the Dirac operator. It naturally applies on it, but it may not be closed. Yeah, so we need to close it, and we get a closure of the Dirac operator. And we will denote the closure of the domain of the closure to be the minimal domain of the D, which is indeed the closure of this space, smooth section vanishing near the corner set of boundary conditions with respect to the graph norm. Here, the graph norm means the D. I will denote this. The D norm is L2 norm plus the L2 norm of the D applied on it. Okay, and this operator D bar actually it may not be essentially self-adjoint. That is because if we consider its formal adjoint, then it will be larger. So let's say D bar star to be its formal adjoint, and its domain will be the following. So we will denote it by the maximal domain of D, which is functions like in L2, and D applies on it also in L2. Here, D phi is defined in the weak sense. Weak means we pair the function phi, the L2 function, with sections in this smooth space. Okay. So far, any questions for the definition of the two domains? Okay. And in particular, for this case, we know that the Dirac operator is at least an elliptic operator. Actually, we really need some estimate, just like what we have done previously. So we can show that by the Guoliang inequality, that the minimal domain is actually exactly the H1 space. So think about it like just recall the green formula we have deduced. The left hand side is the D norm. On the right hand side, we have lots of terms, but roughly speaking, we have a gradient term. So in a very rough word, the D norm can control the gradient. So that will show that the minimal domain is exactly the H1 space. And another point we need is that this so-called codimension 2 singularity is removable for H1 space. So this function of smooth sections, it may vanish near the codimension 2 points, but if we complete it, we will get the whole H1. Even though some smooth function in H1 may not vanish here, but it can be approximated by sections here with respect to the H1 norm. Okay, and here I can introduce the definition of essential self-adjointness. So in general, these two domains are different. Okay, and if they're gray, we'll say that the operator D with respect to boundary condition is essentially self-adjoint. All right. Okay, and from the previous theorems, the importance is that we need to show that it's essentially self-adjoint to compute its index. Okay. So since the manifold looks like a manifold with corners, so if we only look at codimension 1 face, maybe I can draw a picture here. Let's look at the 2D case. If you look at here, for example, if there's really some functions in the maximal domain but not in the minimal domain, okay, suppose that we have such a function, then the function cannot have any bad points near the faces, because we know that the boundary condition is nice. It's so-called elliptic in the classical sense. So the only places that the function can be bad should be the corner points. Okay, so by a partition of unity, we can localize our computation of that function near the 3 points. If there's no obstruction to the essential self-adjoint at each of the points, then we know that the whole operator is essentially self-adjoint. Okay, so now we only need to look at this very lovely angle instead of the whole picture to compute the maximal domain quotient by minimal domain. All right, to illustrate the key ideas, I think it's better to look at the very baby example. So for this angle, okay, all right. Now keep in mind that our space N and M are actually 2D plane, or actually a 2D angle with a flat Euclidean metric, and actually they're the same. All right, the angle for N and M is the same, just alpha. So the boundary condition is also very standard. It's given by the okay, let me write given by the normal vectors from N and M, and here they're just the same vectors. So the bundle we're looking at, just spinor times spinor, is just forms, and the Dirac operator is just a theorem operator, and the boundary condition is the forms does not have a vertical direction, or it's only made by tangential directions. Okay, to study this operator on 2D is okay. This is just a single angle. We can use the method of change of coordinates. So we will have a polar coordinates here described by r and theta, and we can change it from polar to cylindrical coordinates given by this map psi 0 and psi 1. So the psi 0 will map the first copy of forms on the link. Here L stands for the link, this arc, or just a segment. Okay, it's psi 0 will map the first copy to even forms, and psi 1 will map the second copy to the odd forms.
And may I ask you, sorry,
yeah, sure.
May I ask you a question?
Yeah, sure.
So before we looked at sections of the spinor bundle of the domain tensor pullback of the spinor bundle of the target, right?
Yes.
And here you talk about differential forms.
Yes.
So there is some sort of identification going on. How does that work?
Yeah. Oh yeah. Maybe I can write it somewhere. So I think it's classical that for space, the spinor tends for at least even dimensional space, where spinor times spinor is identified with forms. Yeah, like T of n. Okay, and more precisely, this identity given as follows. So and locally we can choose a basis for one of the S, for example, this one. Then every form here, I write it as omega, is mapped to the summation of Si tensor C of omega Si.
Okay, and you trivialize the spinor bundle S and of domain and target in what way?
Let me expand. Here I just look at this baby example. Okay, this baby case is just a 2D plane with flat matrix, so everything is flat. So this definition really makes sense. Okay, right? You agree? So and for the general case, it's this guy is actually neutral. Yeah.
No, I'm also talking about the sector here, and this means you choose a trivialization of S in domain and target, which is which identifies each fiber with a standard model of S, right? Yes. So that it's a flat bundle S and S star.
Yes.
And so these are actually then the spinor representations, fixed spinor representations. And you fix that throughout the proof?
Yeah, at least for this flat case.
Okay, good. Yeah, okay, no, I'm also talking about the flat case. That's okay.
Actually, as I explained, we only need to localize the computation at each of the corners. So
that's
we're not going to do it for globally for the whole manifold, but only at the corners.
Yeah, I agree with that. I'm also talking about the sector, and I think of the sector as being a subset of R2, so to speak.
Yes.
And on R2, of course, we have some trivialization, standard trivialization of S, and the same thing. And you fix that before you start the proof, right?
Yes. Yes.
Okay. Good. Mm-hmm.
Okay. And after all the procedure is done, so we get just forms, and at least for Euclidean space, this identification is standard. Yeah.
Okay.
Okay, all right. And now we have okay. Let's look at only forms, and by this change of coordinates, we can move it from forms to a cylindrical from the polar coordinates to cylindrical coordinates, and we have these coefficients here to ensure that this psi is a unitary with respect to the L2 norm on different spaces. Okay. So for example, if you look at the function, it's just here. You try to integrate in the polar coordinates, you will have the actual term come from the Jacobian. Okay. Now after the change of coordinates, this theorem operator will be turned into this form. Okay. We have a R derivative, and 1 over R is singularity times 0A0. Where this A is roughly speaking the theorem operator on the sector or on the link given by the following. So diagonal, we have a -1/2, and off diagonal is theta and partial theta. Okay. And now let's look at the boundary condition. Okay, recall that the boundary condition means the form only consists of tangential directions or does not contain the vertical, the red arrow. So red arrow is actually exactly d theta. So since the form does not contain d theta, so here we will have this term and this term vanish. And both are exactly the eta here. So actually this standard boundary condition will give us a boundary condition on the link given by eta 0 and eta alpha is 0 for both of the A. Okay. All right. So far, any other questions? Yeah. Now here we want to study the essential self-adjointness, and this comes from the very classic von Neumann theorem on boundary operators. So we want to study the quotient of maximal domain quotient with respect to minimal domain, and this very explicit description of it, and the quotient is given by here, the E plus minus space and E plus space, and this is actually the eigenspace of D in the maximal domain with respect to eigenvalue plus minus I. And also this decomposition is orthogonal decomposition with respect to the norm induced by the graph norm of the inner product with respect to the graph norm of D. Not orthogonal in the L2 sense, but the orthogonal in the graph of D, in the sense of graph of D. Okay. Since we're talking about eigenfunction or eigenvalues, and from basic linear algebra, we know that similar matrices will have the same eigenvalue, right? So the essential self-adjointness of D is equivalent to the essential self-adjointness of the conjugated of it. Oh, by the way, this psi is a unitary, so that it preserves the L2 space. Yeah, so it will preserve the maximal domain. And here the D hat is of this form, and the essential self-adjointness is essential self-adjointness of D hat subject to the boundary condition on each link. Okay, actually, the study of these kind of operators, or more general, some conical operator or conical metric, date back to very early, like I think it date back to Jeff Trigger. There are many papers, many results on it, even on different operators. Here we're looking at Dirac, but we do have some like other series for Dirac or signature or whatever. And when they study the cases of conical metric or conical operators, the key point for the essential self-adjoint is this: the D hat is essentially self-adjoint if and only if the operator A has a spectral gap. In the classical results, the conical or the link is usually a closed manifold, but actually here we have the link is a manifold with boundary, but we still have a spectral decomposition of it, so the proof still goes through. So actually, this theory still holds for our case. Okay, let me briefly explain why we have a spectral gap. Okay, suppose we will try to solve the eigen function, like D hat omega is I omega. We'll try to solve this. So since this A has a nice special decomposition with orthogonal basis of eigenvalues or eigenvectors, let's say omega is given this form, summation of f lambda phi lambda and summation of g lambda phi lambda, where these phi are eigenvalues of A on the link, and F or G are function on R. Now we plug in this omega into the formula, and we will get an ODE F lambda and G lambda disappear for the same eigenvalue. You can imagine, yeah, in plugging that, we only need to take a look at the at the functions, and A applies on phi lambda, which gives the lambda. That would be a parameter in the ODE. We actually parameterize by lambda. Okay, and we'll try to solve it. Well, this is a mathematical series of that, and the solution will give us some so-called modified Bessel function with a parameter lambda. So that's the solution. Okay, thanks to the study for these special functions, and we know that these functions lies in L2. It's a square integrable if and only if lambda absolute value less than equal to 1/2. Okay, in other words, if we have a small spectrum of A, I mean a small eigenvalue or small eigenvector of A, we can construct the pair of F lambda and G lambda so that they're square integrable. So we can construct the solution to d hat with eigenvalue I, and that would be an obstruction of maximal domain and minimal domain, or obstruction of essential self-adjointness. In other words, if A really has a special gap, then any of its solution does not lie in L2. So that would be nice. So because we're looking at the L2 space, so there's nothing there, just the good things. Okay. So far, any question for this? All right. Now we know what we need to do to compute the spectrum. Well, let's recall that this A operator is given by this. We have a diagonal -1/2 -1/2. Off diagonal partial theta partial partial 0. Off diagonal part is roughly speaking the Gromov here. And the boundary condition, the link with eta 0 and eta alpha are both 0. Actually, we know how to compute the spectrum of the link theorem operator by just move away this -1/2. So with respect to this boundary condition, we know its solution. Roughly speaking, this eta should be a sine function, and psi is a cosine. So its spectrum is simply here, the k pi over alpha, subject to the boundary condition. So by adding -1/2 to it, spectrum of A is very clear. It's -1/2 plus k pi over alpha. And more especially, when k is 0, it's -1/2. And when k is 1, with -1/2 plus pi over alpha, which is of this form, 1/2 plus pi minus alpha over alpha. So since we need A has a special gap, this guy is already -1/2, but this guy we need it to be larger than 1/2. So we need to assume that alpha is less than or equal to pi. Okay, so yeah, this condition or this convex condition is really essential here to ensure the essential self-adjointness. All right, so far any questions? Okay, I think this is almost the key point of this article, the key point of the techniques that we try to compute the index, compute the essential self-adjointness. But after we do that, then almost everything is done. So the rest is just a modification of that. For example, if we look at the general case, let's look at 2D case. Okay, M and both of dimension 2. We need some modification near the corners. we know that both M and N, at least the metric in the corner is asymptotic conical with respect to the R direction. But by multiplication, it's actually this asymptotic part does not affect the essential self-adjointness. So after that, we can assume that both the metric G and G bar near the corner are just flat Euclidean. So that near the corner, this spinor, well, it's nothing but a trivial bundle. So just as pointed out, well, we need to decide how to trivialize it, but it's just trivial. Okay, so its pullback is also trivial, and also the pullback, because it's trivial bundle with flat metric, the pullback connection also a trivial connection.
May I interrupt you?
Yes, sure.
And so just to make sure, so you choose a trivialization, a flat trivialization at the beginning of your computations, right?
Well, actually, it does not. In the result, it does not depends on the which trivialization you choose. Actually, different trivialization will differ by unitary transform, yeah, or orthogonal transform, and actually that does not affect the essential self-adjointness.
Okay, of course you can choose a different trivialization after rotating.
Yeah, exactly.
But then at some point you fix a trivialization of SM and the pulled back bundle for your computation.
I will explain how we choose the trivialization.
Okay, good.
Okay. Yeah, thank you for the question. So, but anyway, in the other case, we can choose that so that this bundle is identified with the forms and D is identified with the theorem operator. So now let me explain how to choose it. Okay. The following picture is just a simple way. We just put the two manifolds or the two corners in the same Euclidean space. Well, you may say one of them may differ by a rotation. Yeah, right. But let's pick one because the rotation actually does not affect the essential self-adjointness. Because that's where we just conjugate for the Dirac operator. So to talk about its eigenvalue, eigenfunction, this makes no difference. So so the trivialization is chosen so that we put the two angles in the same Euclidean space. So that we identify the two spinors or the two tangent bundles is just like parallel transport. Okay. For example, at this point we have a vector here, and we can parallelly transport to this point to identify the spinor of N with spinor of M by the parallel vectors. Okay. Does this answer your question?
Yes, so you choose the trivializations in such a way that U1 is equal to V1, right?
Yes.
So that's what the picture says.
Yes, this is just for convenience. Yeah.
Okay, good. Okay, so you choose your trivializations in your computations in such a way that U1 is equal to V1.
Yes.
Is that correct? Okay, good.
Yes. Yeah, but I want to emphasize that it's just for convenience. We can choose a different, but the essential self-adjointness, the result will be the same because they're just up to a unitary transform. Okay, but keep in mind that if this vector is agrees, then the rest of things, because there's just the same Euclidean space, will be just parallel transport. So now the boundary condition will be given of this form, this new boundary condition. And here they used to be the normal vector. So say, but now it's just the vectors come from the two edges, U1, V1, U2, and V2. And we choose a way such that the bottom edge are parallel, but actually this does not make too much difference. You can also choose a different way, and the computation is exactly the same. Okay, so now we can do the same thing as previously. We try to find the theorem operator in this sense. Do the change of coordinates. We look at the link part. It's roughly speaking the theorem operator with some diagonal elements. The boundary condition is weird now. Okay, for example, in the previous choice, we choose U1 is equal to V1. So at the point of 0, the boundary condition will be just as we talked about previously, eta is 0. But at the top, okay, here the angle of here this is angle alpha and this is angle beta. The boundary at the top is looks like yes, here it's a combination of cosine and eta, and alpha is 0. Well, it's roughly speaking, it's some kind of Lobby boundary condition on the arc or on the segment.
Well, I guess that's really the one of the requirements.
Oh, sorry. Any questions? Am I? Did I hear anything? All right. Okay. And with this boundary condition only on the segment, this operator A is also essentially self-adjoint, and we can talk about its eigenvalues. So same proof will go through, and the D is essentially self-adjoint if and only if A has a spectral gap 1/2, subject to the boundary condition. Okay, now what we will need to do is to compute the spectrum of A. Well, here's just a straightforward computation, and we can show that spectrum of this A is exactly given by minus beta over 2 alpha plus k pi over alpha. For example, when k is 0, this is minus pi beta over 2 alpha. And when k is 1, I will get this 1/2 plus 2 pi minus alpha plus beta over 2 alpha. Okay, we assume that everything is convex, so beta is less than or equal to pi. So if we still want A has a spectral gap, then look at this spectrum. We need it to be we need its absolute value to be greater than 1/2, so that will give us alpha is less than or equal to pi. And also, if alpha is less than or equal to pi, then we have alpha plus beta is less than 2 pi. So this spectrum is greater than 1/2. So as a summary, if alpha is less than beta, and then we will have the essential self-adjointness. And just to remind you, this is exactly the angle comparison condition. Okay, I think so far we have already solved the Gauss-Bonnet theorem using this method. Okay, but let me briefly talk about the higher dimensional case. So look at the picture here. So for example, 3D, we have two different types of singularities. One is here on the edge. So on the edge, it's actually the singularity part comes from the directions that is vertical to the edge. So the metric here can be regarded as let's say asymptotically fiber bundle of a conical metric. So there's a very classical result on that. So for the fiber-wise conical case, the analysis is exactly the same. So the condition is exactly the same, and we also have this 1/2 there. And we already know that from the angle comparison condition, there's no obstruction of essential self-adjointness near these types of edge.
May I ask you something here?
Yes, sure.
And I think in this part of the argument, you again have to choose a trivialization of your spinor bundles, right?
Yeah,
flat trivializations.
Yes.
And now, so when we are in this upper corner, you have to somehow compare your boundary conditions.
Yes.
B with kind of similar boundary conditions inside the link.
Oh, yes, exactly.
So, and for that, okay, so how do you do that? Can you explain that?
Okay, maybe I'm not sure if I understand the question correctly. So the boundary may be like somehow curved here. So the boundary condition, okay, on the link will also be weird, and the boundary condition here will also be like crazy. But at least asymptotically, the metric is Euclidean.
Sure. No. We are talking about the flat case. I'm not talking about the curved case.
Yes. Okay. All right. Then that's the flat. Oh, if we only talk about the flat case, then that's better. Then that would be just the standard flat corner. And if you look at another flat corner here, we put them in the same, for example, 3D space. Then we can choose the identification like this. by parallel transform.
Okay, so maybe I state my question more precisely. So we have the boundary condition B on the three-dimensional sector.
Yes.
And then you take the link, and you have these three angles, and you have your operator. I don't know if I think it's called P or the Dirac operator. And you, at some point, you have to compare the two boundary conditions in order to perform an induction. And at least if I read your paper correctly, then, for example, if you look at this upper corner, you choose your trivializations of your spinor bundles in such a way that so you have four vectors and they all lie in the plane, in the tangent plane of the link at the upper corner. And then you argue that the boundary conditions in the three-dimensional case and in the two-dimensional case on the link coincide.
I know what your question. So are you asking about this? So in the higher dimensional, can we do the same thing as U1 is equal to V1?
Right, yes.
Yeah, that's a very nice question. So here I apply the computation or apply this assumption. It's just for convenience. We can also consider different types of boundary condition like this. We put the angle in a very crazy different position. So that would be different choice of trivial addition as in your question. And here we have the boundary condition here, and we have a normal vector here, and we just parallelly transform part it from here and whatever. But the essential divergence will be completely the same as here. The condition is the same because this picture and this picture only differs by a unitary or by a orthogonal map.
Yeah. But so I think in higher dimensions,
exactly the same.
But in dimension 3, the choice of the trivializations is no longer just for convenience, but you have to make sure that all your angles are in the tangent space of the upper vertex point.
Yeah, maybe we can maybe this will convince you if we really do a computation here for this boundary condition, right? Yeah, maybe this will convince you if we really apply the computation for arbitrary trivial addition.
Maybe can I make a comment?
Yeah.
So Bernard, you see in a three-dimensional case, when you look at the bundle restricted to the two-dimensional link, the boundary condition actually doesn't have to be tangent to the link because you already double the bundle. So actually, all this computation, the boundary condition, you don't need it to be tangent to the link, actually.
Right, but so in your paper, you bring it in a situation where the four normal vectors, two belonging to the domain and two belonging to the target, are tangent to the link in order to make an argument that the boundary conditions...
We don't have to assume that.
Yeah, but then I do not see how the argument works, because in dimension 3, the situation is much more complicated than in dimension 2.
Even in the 2D case, in this picture, this V2 has nothing to do with the link. It can be not tangent to the link.
Right, but we see already in dimension 2, so for example, one vector, the vector V2, is not tangential to the link, right? And this creates a sort of boundary condition which involves the angle of these two vectors in your boundary conditions. And this is why it appears in this computation, which I can follow. There's no problem with this computation. But now in dimension 3, the situation is more complicated. So if you choose different trivializations of the spinor bundles SM and SN pulled back, then so the vectors are no longer tangent to the link, and then I think the argument becomes more complicated, and I didn't see it right. I think we agree that for the whole computation you have to stick to one trivialization of your bundles. You cannot choose trivializations depending on your vertices.
Yes, I agree, and maybe. Let me see if I understand your question correctly. So for here, like this picture, this angle here is actually exact the difference of the angles, but here we have the angle 0, so that makes sense for the difference. But if we choose a different trivialization, we will have two angles on both U1 and U2, right?
Yeah, no, in dimension 2, it's fine. I agree with dimension 2, no problem.
Yeah, well, even higher dimension, if we still have the difference, like two. Well, let's look at the picture here. Okay, if we still have the two angles not match well, but the computation actually exactly the same. We will get a Robin boundary condition of both the points, a Robin boundary condition, or a mix of the psi and eta on both points, and the essential selfness, the results will be exactly the same. Only, roughly speaking, the essential selfness only depends on the relative position of the normal vectors.
Right. Yeah, but that's exactly the difference. If you have, if you are in dimension 2 and you have two vectors and you apply a rotation to it, then the angle of the two vectors doesn't change, of course.
Yeah.
I mean, this is clear. Yeah. So of course, even if U1 is not equal to V1, you have a certain angle, and the situation is pretty much the same as here. But in dimension 3, the situation is more complicated.
Oh, okay.
So because if you change the trivialization see, look, you have two vectors in the domain and you have two vectors in the target. You have altogether 4 vectors.
Yes.
And now you change one trivialization by a rotation, then the angles, the mutual angles between the vectors, they change not as easily as in dimension 2. Because you just...
But we have to identify, for example, the fiberwise case, we have to assume that these two edges are, for example, put in a parallel way. Maybe we can assume that, right?
Sure, no, that's no problem. I'm just looking at this.
And under that assumption, they will only differ by a rotation.
Wait, but not in the higher dimension, in this case, in the standard case, isn't everything is linear?
Yeah, it's linear. And so, I mean, what we have here is you have two.
So along each phase, the boundary condition is constant. Yes.
Yeah, no, that's clear. It's a linear algebra thing that I'm talking about.
Yeah.
Mm-hmm.
That's no problem about that.
For example, if we put the two edges are parallel in the same space, then our choice is only restrict to a rotation in 2D.
Yes, this is true for this one edge. What is it? Edge. Yeah. But now, if you look at another vertex, then you have to do it differently.
Yes, you're right. So actually, we treat them independently. So if we really need to look at the 3 points altogether, it happens when we look at this point.
Right, but you cannot choose different.
I will explain the computation about this point later. But at least for the away from this point, you agree everything is correct. Yeah.
In dimension 2, you mean?
I mean away from this point.
Away. Oh, okay. Yeah.
Is it fine? It's fine for you. Away from this point.
We can perhaps discuss this point after the talk.
Sorry?
We can perhaps discuss this point further after the talk.
Okay, we can do that.
Yeah, sorry, I just...
Oh, okay. Oh, yeah, thank you. Thank you. Thank you for the comments and questions. Okay, so here maybe I should emphasize this away from the points, from this point, then you can treat the 3 edges independently so that we don't have to look at the interaction of each other, just look at independently. So we have the essential depth near that. So near this point or near the vertex, we need to use to treat it as a 3D conic metric. So here, the link will be simply a sphere, a part of a sphere. And after the unitary change of coordinates, we get also a formula like this, where A is operated on the sphere. And here is everything only differed by maybe a maybe up to a unitary transform in R3, but that does not too much matters. So, and the off-diagonal part is roughly speaking the theorem, and diagonal part is some constants with this number. Okay, so our goal is to show that this, so at least on the link, which is part of sphere, we know that this A operator is already essentially self-adjoint. Okay, with the boundary condition given on the link. Because on the link, at least near, for example, this point, it's a high school math that this angle here is exactly the dihedral angle, because roughly speaking, the sphere is vertical to the edge. Okay, so the operator A will have a nice spectral decomposition, so we can apply the same thing to compute the spectral gap. Okay, so a very is there any question? Oh, okay. Yeah, thanks. So yeah, roughly speaking, the operator A, we need a spectral gap greater than 1/2. Okay, so the diagonal entry CP with P0 is about L minus 1/2, minus 1/2, and when P is L minus 1 is also large. So roughly speaking, this CP will enlarge the spectral gap by its absolute value at P forms. And we see that this number is large if P is at the bottom or at the top. And as for the middle, we have the Guoliang estimate. That is the sphere is positively curved, so that the theorem operator we have a spectral gap, roughly speaking. So, or in other words, the Hodge Laplacian is greater than, has a positive, it's positive, strictly positive with the lower bound like this. Okay, this is just a rough idea of the following lemma, and there will be more computation on that, but the condition is here. So if we still have the angle condition, and which implies that A is self-adjoint on the link, then we have the spectral gap of A is large, regardless of the boundary condition on L. No matter how we apply the boundary condition on the boundary of the link, we have, at least in the picture, 3 edges. No matter how we apply things on that, these operators always have a large spectral gap. In particular, when L is 3, then this is square of 2/2, which is greater than 1. All right, so here we have done everything from 2D to 3D, and then you can do an inductive process from 3D to 4D, and to 4D to 5D, and so on. Then you get everything, so that's the essential self-adjoint. So now let me summary the proof of it. So from the angle condition, we did that D is essential self-adjoint with domain the H1 space, and from the Fredholm, and the index is non-zero, so we can find a solution at least in the H1 space. So the angle condition really ensures that the solution lies in H1. If without it, maybe somehow we can still find a solution, but it will lie in something else and may diverge at the corners. So for sections in the C00 space, I will remind you that these sections are vanished near the codimension 2 faces. So the formula, the green formula, will not have angle term. But all of the terms, 1, 2, 3, 4, are continuous with respect to H1 norms where we can approximate it. So this inequality holds for everything in H1. Therefore, we can conclude that, okay, since from the scalar curvature comparison, mean curvature comparison, we get phi is parallel, or it's nabla phi is 0. And on this smooth manifold, we have a parallel solution. Now it's smooth. Here, smooth means it's not only smooth in the interior, but also to the continuous to the boundary, or even smooth to the boundary. And hence it's non-zero everywhere. So we can conclude the comparison of scalar curvature, mean curvature, and dihedral angles. Okay. All right. That's all for talk today.